Well, will you look at that? We've made it to Chapter 8. You'll be happy to know that most students find the material in this chapter easier than the material in Chapter 7, in part because it's much more geometric, so you can get your head around it much more easily. And there are more problems of the style you are used to in previous calculus classes, where you just have to compute something. But there are pitfalls here as well, and very often those who fall into them do so because their grasp of the prerequisite material, especially trigonometry, is shaky. So since this first video, which covers the first 3 sections of Chapter 8, introducing polar coordinates but without any calculus yet, since this stuff is fairly straightforward and probably familiar to many of you, I'm going to try to build in a little more trigonometry review than I normally might as I talk about this material. Now, you don't need to have every single thing from a trigonometry class at your mental fingertips. I mean, should you know the law of cosines? Well, of course you should know it. It's a generalization of the Pythagorean theorem. It's like the Pythagorean theorem with a little error term. But is it going to be the end of the world if you don't know it off the top of your head for this class? Not really. Or should you know the sum identities for sine and cosine? Again, of course you should. They're pretty basic. But is it going to be the end of the world if you don't know them for this class? No, not really. However, if you have trouble thinking about the trig functions themselves, how they're defined, how they behave, is that the end of the world? Well, no, it's not the end of the world, but realistically, it might be the end of your prospects in mathematics-based courses if you don't get that under control. So if that's you, please do so. Fortunately, trigonometry is a tight, compact subject, so it's easy to master the basics pretty quickly, but you do need them. Anyway, let's jump in and talk about polar coordinates, and we'll review the trigonometry as needed. I'm going to assume you've already read the material or have encountered polar coordinates somewhere else in a previous math course or maybe a physics course, but the basic idea is pretty simple. Instead of imposing the familiar xy coordinates on the plane, which allows us to give addresses to points in the usual way, for example, if I have this point, I might say, well, that's 1, 2, 3, 4 units to the right and 1, 2, 3 units down, so we're going to call that 4 minus 3. Those guys are usually called Cartesian coordinates, after Descartes, or they're sometimes called rectangular coordinates, in the sense that every point determines a rectangle like this. But anyway, instead of having Cartesian axes, the idea is you have a point, the pole, and you have a single polar axis, and then any point in the plane gets its polar coordinates in the following manner. Its first coordinate is simply its distance from the origin, which we call r, and its second coordinate is the angle we have to rotate the polar axis through to hit that point, and we call that theta. So we'd say the polar coordinates of that point are r theta. The r comes first, the theta comes second. Typically, theta is measured in radians. You can use degrees as well, but then you have to specify that this is 47 degrees or whatever. The default assumption otherwise is that this is measured in radians. Now, an important distinction between the Cartesian coordinate system and the polar coordinate system is that once I've laid down my axes in the Cartesian system and specified my unit on each one, then the coordinates of any given point are unique. This point is 4 minus 3, and that's all there is to it. That's not the case with polar coordinates. For example, suppose we have our polar axis here, and we want to specify the polar coordinates of this point. I can't really say the polar coordinates, because there are many pairs of polar coordinates that serve to identify this point. The most obvious one is, well, it's 3 units from the origin, and I rotate through an angle of pi to get there. So these coordinates do the job nicely. And indeed they do. Those are the most natural pair of polar coordinates we could use there. But we could just as easily refer to that as 3 minus pi, since a negative angle just indicates that we're rotating in the clockwise direction. And indeed, we could just as easily say it's 3 pi, because an angle of 3 pi is a full rotation of 2 pi plus another half turn of pi. And clearly there are infinitely many values we could put here for the theta coordinate that will take us there. We could have 3 5 pi, or 3 7 pi, or 3 9 pi, or 3 negative 113 pi. And you might say, well, at least the first coordinate is unique. But that's not the case. It would seem so, but we use a convention that allows us to have the first coordinate negative if we interpret it in a particular way. I think it helps to understand this if you think about polar coordinates in a kind of dynamic manner. I like to imagine when I see r and theta that these are a set of instructions on how to get to a point. And I imagine that we have this rotating ray that starts at the polar axis, and it rotates until we get to theta. This kind of gives us the instructions. Stop when you hit theta. And then once we've reached angle theta, that's when this first coordinate sends instructions, so to speak, to shoot out a point along the ray and have it stop when it reaches a distance of r. So first we rotate through theta, but the point is still waiting here at the origin. Then we fire it down to a distance of r where it stops. Okay, so what would a negative value of r mean? This would probably be easiest to see with a concrete example. So let's consider the polar coordinates -2 pi over 2. Well, to get there, we rotate this thing until we reach pi over 2, well, we know where that is, and then we're going to fire our point out down this ray a distance of -2 units. Well, I know what 2 units is, and I bet you can guess what -2 would signify in this case. It just means that we're shooting it the wrong direction, out of the back of the cannon, so that we would end up here. So this point right here, we could say has polar coordinates -2 pi over 2. Now you might say, well, wouldn't it be much more natural to call it, say, either 2 minus pi over 2, or maybe 2 3 pi over 2? Those seem much more sensible. And I agree with you. If we just wanted to come up with a pair of polar coordinates for this point, my first instinct would be to gravitate towards one of these two. But this one is also acceptable and shows what we mean by a negative r value. So anyway, coming back to this case, which is what I first started talking about, we could give this point some polar coordinates where r was negative. -3, 0 would do the job, for instance, because we haven't rotated the polar axis at all, so we're pointing in that direction, and we go -3 units in that direction, which would be 3 units in the opposite direction. Or for that matter, -3 2 pi would work. Well, you get the point. Polar coordinates have this intrinsic messiness to them in that every point can be represented infinitely many different ways, unlike the good old Cartesian system where each point has a single representation. This might seem like a huge disadvantage for polar coordinates, and it does indeed sometimes cause some headaches, but there's some really nice mathematics that comes out of these different representations, mostly connected with complex numbers, which are intimately connected to polar coordinates. Maybe if we have time, we can talk about that sometime in this chapter. But not right now, just the basics for now. Since we now have these two different languages for working with coordinate geometry, we do need to know how to go back and forth between them, so I want to say a few words about conversion formulas, equations that relate polar coordinates to Cartesian coordinates and vice versa. Let me just take a minute to review some very fundamental trigonometry. If we have a right triangle whose hypotenuse is r and it has an acute angle theta, you should know without an instant's thought how to express the two legs of the right triangle in terms of r and theta. This is really like week 1 of trigonometry. And if you've had any physics at all, you'll surely know this from decomposing vectors into their constituent parts. I'm almost hesitant to review this, it's so basic, but I think a few of you may need it. In a setup like this, the side opposite the given angle is r sine theta, and the side adjacent to it is r cosine theta. This is a picture you should know as well as anything, as well as the Pythagorean theorem, as well as the multiplication table. It really is that basic. Now, where does it come from? It just comes from your old friend SOHCAHTOA. If we didn't know this, if we were in that first week of a trigonometry class, and we said we have a situation like this, and we wanted to know, well, what is that length right there? Well, how would you figure it out? You'd pray to SOHCAHTOA. Oh, great SOHCAHTOA, please help me. And he would inspire you and make you realize, you've got this angle in a right triangle, and you know the adjacent side and the hypotenuse. So SOHCAHTOA, adjacent and hypotenuse. That means the cosine of theta is that adjacent side over the hypotenuse. And now if we clear the fraction, we get x equals r cosine theta, just like I said it was a moment ago. And of course, you would solve the exact same problem over here, and you would find that this length is r sine theta. So you end up with this picture. And that picture will take you halfway to your conversion formulas, because I should mention that the convention is the very natural one that we are superimposing the two coordinate systems, and we are taking the pole of the polar axis to be at the origin, and the positive x-axis to be the polar axis. We could, in theory, do something different, like that for the polar axis, in which case we'd need entirely different conversion formulas. But there's no reason to do that, so we don't. Anyway, so let's suppose that we have a point in the plane and we know its polar coordinates, r and theta. So I'll draw in r and theta. Those are known, and we would like to know its Cartesian coordinates. So what we're doing here is going to be polar to Cartesian. We know the polar coordinates, we want the Cartesian coordinates. Well, the Cartesian coordinates at this point should be obvious to anyone who knows this first week trig picture. Drop a perpendicular. Well, here's the x-coordinate of that point, and here's the y-coordinate of that point. What's x? Well, by this picture, x is going to be this hypotenuse times the cosine of this angle, hence r cosine theta. Similarly, what's y going to be? The hypotenuse times the sine of that angle, so r sine theta. And those guys are our conversion formulas. There's nothing deep about them. They're just this old, familiar picture from trigonometry. And yet, am I pulling the wool over your eyes? I showed you that these formulas make sense when the point is in the first quadrant. But what if I take a point that's not in the first quadrant? Most points, after all, are not in the first quadrant. The first quadrant only takes up a quarter of the entire plane. Do these still work? They had better. They do still work, but please don't just take that on faith. Not because someone might be lying to you about it, that's not true, but because understanding why these hold when this is in other quadrants will ensure that you understand some basic things about trigonometry. The sorts of things that I said really are essential. Not just having a formula memorized or something, but really understanding what sine and cosine are. So let's go through it in detail when the point is in some other quadrant. Let's consider a point, say, in the third quadrant. So let's say I've got a point right here, and I know it has polar coordinates r and theta. That tells me that this distance right here is r, and that this green angle is theta. And the question is, what are its x and y coordinates? Are they actually given by these equations? And the answer is yes. The punchline is not surprising here. But why is that so? We saw why that was so in the first quadrant. We just drew that trigonometry familiar formula. But why is it so here? The answer is slightly more involved, and you should understand it. Not for the sake of this particular problem, but for the sake of understanding trigonometry. So let's make sure we do understand. The claim is that if x and y are the Cartesian coordinates of this point, which has polar coordinates r theta, then these equations hold, even though this is in the third quadrant. Why is that so? Well, the first thing to recognize is that since this point is in the third quadrant, both x and y are negative numbers. That means that if I drop this perpendicular here, this length, being a length, and hence a positive quantity, is not x. X is a negative number. That length has the same magnitude as x, but an opposite sign. So that length is minus x. And similarly, that length is minus y. Okay. Why am I doing that? I'm doing that because I'm trying to construct this little right triangle right here. Much of trigonometry can be reduced to right triangles, as you know. So I'm going to do my analysis on that right triangle. But in that case, I need to know something about one of its acute angles. Let's say this one that I'm putting in red. What is that angle? It's not theta. Theta doesn't lie in any right triangle. It's too big. But what is that red acute angle? Well, if we took theta and subtracted off this half term, which is pi, we would obviously get the red angle left over. So that angle is just theta minus pi. Well, this is good. Now I have this right triangle, and I know about its sides, and I've got an acute angle. If I want to come up with some kind of formula for x involving r and theta, well, now I can see how to go about doing it. By basic right angle trig, i.e. that familiar, I hope, picture I mentioned before, by basic right angle trig, I say, applied to this right triangle, we see that minus x, the leg of this right triangle that's adjacent to this red angle, what's that going to be? Well, that's going to be the hypotenuse times the cosine of this angle. Thus, this stuff. Well, we've got a good foothold now, because I have an equation connecting x to r and theta. But the first thing you might say is, hey, wait a second. This is minus x. That's ugly. I agree. Let's go ahead and multiply both sides by -1. Done. All right, now I have x in terms of r and theta. And you could say that in one sense, we're done, but in another sense, we can clean this up, at least if we understand trigonometry. One option would be to use that sum identity for cosine that I mentioned earlier. That would work here, and I encourage you to try that. But I want to show you another path that will help us review much more fundamental ideas about trigonometry. It's unfortunate that this is theta minus pi. Pi minus theta would be a lot easier to work with for reasons that will become clear in a second. But hey, we all know algebra. We're going to force the issue. How can I make this into pi minus theta? Just factor out a -1 inside these parentheses, and I end up with this. Right? That's pretty common algebraic trickery. I can always turn a minus b into b minus a if I stick a negative outside the whole thing. Anyway, that's particularly useful here because now I've got cosine of minus something. And what do I know about cosine of minus anything? Well, that, I hope you know in your very blood, is cosine of that thing, which is another way of saying that cosine is an even function. That's what it means to be an even function. It absorbs factors of -1. And very quickly, why is that? Think about the unit circle. If I have some angle, star, and I also look at minus star, then what do I know about the cosines of those things? Well, cosine is the x-coordinate of this point. So what do I know about the cosine of star versus the cosine of minus star? Well, obviously, those things have the same x-coordinate, which is why they have the same cosine, which is what makes cosine an even function. Anyway, that means since I've got cosine of minus something, it's just cosine of the something. Good. Now I've got cosine of plain old pi minus theta. And that's something that I can also get in about 2 seconds by thinking about the unit circle. If I have some angle theta, wherever it may live, and I want to compare it to pi minus theta, its supplement, well, that is going to be something like that angle, pi minus theta. And what do I know about the cosine of theta versus the cosine of pi minus theta? Well, we just said cosine gives us the x-coordinates of those points. Are they equal? Do these have the same x-coordinate? Of course not. One is positive and one is negative. But even though they differ in sign, they have the same magnitude. So the cosine of this is equal but opposite to the cosine of that. In other words, cosine of pi minus theta is equal to negative cosine theta for all theta. Now, no one in his or her right mind memorizes this thing. Not because it's hard to memorize or anything like that, but because it's superseded by a basic knowledge of trigonometry. If you understand what cosine means, you can draw this picture and recover it in 2 seconds whenever you need it. Now, in an actual trigonometry class, we'd be very careful to ensure that this holds in all 4 quadrants again. It does, but we'll take that as read. We're going to use that identity up here, which means that where I have cosine of pi minus theta, I can replace it by minus cosine theta. Well, now these 2 negatives cancel out, and I'm left with x equals r cosine theta, exactly as we said it should be. Good. And of course, we can do the same thing to show that this y is going to be r sine theta. And I encourage you to stop the video for a moment and do just that. Did you do it? I hope so. If you did it successfully, you'll know that you had to use the fact in there that sine is an odd function. And if you did not succeed, well, now you have a hint. And there's a homework problem that asks you to do as much in the remaining quadrants, 2 and 4. Okay, as I say, that's very good trigonometry review. And it takes care of our first set of conversion formulas from polar to Cartesian. But what if we're going the other direction, from Cartesian to polar? In other words, we have some point, and we know its Cartesian coordinates, which in this first quadrant case would tell me that that length is x and this length is y. What can I say about its polar coordinates? R and theta, what do I know about them? Well, I can come up with those, again, by drawing a simple picture. Let's try to draw them in here. If that's r and that's theta, then I want to know how is r related to x and y, and how is theta related to x and y? Well, the first one's very easy. R is related to x and y by the Pythagorean theorem. So r squared is x squared plus y squared. And here it's very natural to say, hey, why don't you just take the square root and say r is the square root of x squared plus y squared? You can do that, but you have to be careful because you have plus and minus here when you take those square roots. I do want to allow for the possibility that r is negative. So we usually just leave it in this form, which is often, anyway, much more convenient when we're translating not just points, but whole equations over. All right, and what about theta? How does theta relate to x and y? Help us, O great SOHCAHTOA. Oh, we've got the opposite and adjacent sides. Of course, that's the tangent. So we know that the tangent of theta is y over x. And that's our other conversion formula. Hey, wait a second, you might say here too. Just solve for theta, will you? Shouldn't that be theta is arctangent of y over x? Not so fast. There's a very good reason for leaving that as is. And this may necessitate a little more trig review about this function arctangent. Let's box this up so that our quick review of arctangent doesn't mess anything up. The three inverse trig functions, arccosine, arcsine, and arctangent, all have restricted ranges, and it's important to bear that in mind. The expression arctangent of whatever means something. What does it mean? It's very tempting to say, oh, arctangent of star, that's the angle whose tangent is star, right? Careful, careful, careful. That's half the definition. It's a crucial piece of the definition, but it's not the whole thing. The problem is that there are many angles whose tangent is whatever you want. For example, if we were interested in, say, the arctangent of 1, and you said, well, that's the angle whose tangent is 1, right? Well, which one? There are a lot of angles whose tangent is 1. I mean, pi over 4 is one of them, because we know we can interpret tangent as the slope of this line. So tangent of pi over 4 is 1. But it's also true that tangent of 5 pi over 4 is 1. And for that matter, it's true that the tangent of whatever that is, minus 7 pi over 4 is 1. And the tangent of 9 pi over 4 is 1. There are lots of angles whose tangent is 1. If arctangent is going to be a genuine function, the whole idea of a function is you put one thing in, you get one thing out. One in, one out. So arctangent has to specify which one comes out. It has to be unambiguous. And so we specify it. We say that arctangent is the angle in the interval minus pi over 2 to pi over 2, whose tangent is whatever, 1 in this case. So if we're looking for arctangent of 1, I can't say, oh, it's 5 pi over 4, because 5 pi over 4 does not lie in that interval, nor does minus 7 pi over 4 or any of the other ones we were talking about. The only one that lies in that interval is pi over 4, and that's why that is the arctangent of 1, because its tangent is 1 and because it lies in this specific interval. That same interval we use for arcsine, but for arccosine, it's a little different. We go from 0 to pi, and I'll leave it to you to remind yourself or figure out why we have to change it for arccosine. The point is, if I tried to rewrite this and say, oh, theta is arctangent of y over x, that's not always going to work, because that would be claiming that theta, by virtue of being an arctangent, must be something between minus pi over 2 and pi over 2. But that doesn't make any sense. That would mean that the conversion formula would only work for points in quadrants 1 and 4. So if you try to turn that into theta is arctangent of y over x, it's not going to work for any points that are in quadrants 2 or 3. You do have to make use of some basic geometric understanding to use these formulas. Okay, anyway, those are the conversion formulas. What I'm trying to get across here is these aren't just 4 things to memorize. They are things to understand, to relate to things you already know, to use as an excuse to review trigonometry that hopefully you already know, but maybe you don't know as well as you should. One last thing about these conversion formulas. I caution you not to get overly enthusiastic about them. Don't ever forget when you're working with polar coordinates and you're trying to convert over to Cartesian or vice versa, to think about what's going on, to visualize it. You may be able to see in a moment what's happening. And appealing to formulas like this is redundant at best and just kind of tacky. I'll give you an example to see what I mean. Suppose you sit down to take a test or something, and you're faced with this question. If a point's polar coordinates are 2 pi over 2, find its Cartesian coordinates. Now, one solution is to say, oh, I've memorized these conversion formulas. Let me use them. Okay, so x is, that's r cosine theta. So that's going to be 2 cosine pi over 2. What's cosine pi over 2? Oh, let's see, that's 0. So that's 0. And y? What did I remember? That's r sine theta. So here r is 2 and theta is pi over 2. r 2 sine pi over 2. What's sine pi over 2? That's 1. So that's 2. So the Cartesian coordinates are 0, 2. Okay, put that on your test. You got to check. You get the answer right. But come on, this is a very tacky solution. This looks like the solution of someone who isn't stopping to visualize what's going on. It's not wrong. I want to emphasize that. But solution 2 is much better. Just sketch a quick picture. If the polar coordinates are 2 pi over 2, where does that live in the plane? Well, think about what that means. We rotate through pi over 2, and we shoot the point 2 units down, so that takes us somewhere here, 2 units away. Okay, what are the Cartesian coordinates of that point? Well, obviously, they are 0, 2, and that's the end of the story. This is an example where a picture is indicative of more insight into what's going on than all of those equations we had before. They both arrive at the right answer, so that's good, but don't forget to stop and think about the meaning of the question you're being asked. In the same spirit, let's do a second question. If a point's Cartesian coordinates are -1, 1, find polar coordinates for the point. Well, one thing you might do is say, gotta remember my conversion formulas. What are they? I worked so hard to memorize them. R is the sum of the squared Cartesian coordinates. That's going to be square root of 2. And theta is going to be arctangent of y over x. Not heeding my warning. Well, 1 over -1 is -1. Arctangent of -1. That's minus pi over 4. So the polar coordinate's going to be root 2 minus pi over 4, right? No, that one's wrong. Don't do that. I wasn't joking when I talked about arctangent. Thinking through this geometrically will show you why this is wrong. Where does that point live? We're at -1, 1, right here. Where does this point live? If theta is minus pi over 4, that takes us that way, and square root of 2 would shoot us down to some point out here, which is clearly the wrong point. So what went wrong? It was that arctangent. As I said, arctangent will always deliver a point in one of these two quadrants. It cannot get to a point in this quadrant. So if you are going to take this approach, which is not what I advise, you would need to say, instead of all that stuff, tangent of theta is 1 over -1, which is -1. And then you would have to think geometrically what that value of theta would have to be to get the point in the right place. So you have to think geometrically even if you go with these formulas. But with such a simple point, these formulas are overkill. Just think about it. We know where it lies, right here at -1, 1. What are the polar coordinates of that point? Well, the distance from the origin is obviously square root of 2, just by Pythagorean theorem on that triangle if you like. And what's that angle? It's a right angle plus pi over 4. So that's going to be 3 pi over 4. And therefore we can have an r value of root 2 and a theta value of 3 pi over 4. And we've got it. And once again, this picture indicates much more understanding than what we were doing before. So don't forget what's going on. And even if you do use these formulas, which sometimes you will need to, make sure you're still visualizing things so that you can pick, for example, the appropriate angle. Okay, I think that's enough on the conversion formulas. Now we need to spend a little time talking about polar graphs. I don't have too much more to add than what I've written in the book, although I will say that it's usually interesting in any coordinate system to think about the simplest graphs, which you get when you hold one of the variables constant. For example, in the Cartesian coordinate system, if we hold a value of x constant, like if we say x is 2, then of course the graph looks like this, because this is the set of all points in the plane whose x coordinate is 2. And similarly, if we just hold y constant, well, the graph of y equals 1 looks like this, a horizontal line, because this is the set of all points in the plane that have y coordinate equal to 1. If we do the same kind of thing in the polar coordinate system, we might consider the graph of something like r equals 2, where there's no condition on theta, we just want r to be equal to 2. Well, it's pretty clear that would be a circle of radius 2, because every point on this circle has polar coordinates that satisfy this equation. Although there is actually a subtlety here, at least when we compare this to our familiar Cartesian coordinate system. When we were looking at this vertical line, the graph of x equals 2, every point on that line has x coordinate 2, and every point not on that line has some different x coordinate. That's the algebraic condition that separates points on the line from points off the line. And the uniqueness of the representation makes it especially nice. This point has Cartesian coordinates 2 pi, and that's it. As I said at the beginning of this video, that's not quite the case with polar coordinates, because each individual point has infinitely many different representations. So for example, this point has the representation 2 pi over 2, which satisfies this equation, and this representation, 2 minus 3 pi over 2. Well, it still satisfies the equation, but Minus 2 minus pi over 2, which is another representation of this same point, does not satisfy this equation. And that's perfectly okay. We say that as long as a point has at least one representation that satisfies an equation, then that point is on the graph of that equation. It's a subtle difference, but it does occasionally make itself felt. Because, for example, if you just saw this polar representation of a point, you might say, well, it doesn't satisfy that equation, and therefore the point corresponding to this doesn't lie on the graph. But that would be wrong. That sort of thing will never happen with Cartesian coordinates, but it can happen here. So you have to be careful. It's not a problem that often comes up, but it certainly can. So it's just something to bear in the back of your mind. A point lies on the graph of a polar equation if it has at least one representation in polar coordinates that satisfies that equation. It may have some representations that do not satisfy the equation. That's okay. As long as one of them does, it's on the graph. Okay. Oh, and what if we have a polar equation that doesn't involve r? That's just something like theta is held constant, let's say at pi over 3. What does the graph of that thing look like? Well, that would be the set of all points with at least one representation where the theta coordinate is pi over 3, where that angle is pi over 3. Well, pi over 3 looks something like that, so any point on this ray clearly has a representation that satisfies this. I mean, we could have 2 pi over 3 or 4 pi over 3 or whatever, but is that it? Is it just this ray? No, it also includes the rest of the line on which it lies, because points on this side, like this one, could still be represented with a pi over 3 in the theta slot, as long as the r slot has a negative value. Of course, this point can also be represented by things like 2 4 pi over 3, a coordinate pair that does not satisfy this equation, but that's okay, because we know this point has at least one representation that does satisfy it. So it is indeed on the graph. And these boring constant graphs make up a kind of grid. With Cartesian coordinates, you get ordinary graph paper, where you can think of every line on the grid as being some constant function, x equals a constant or y equals a constant. And the analog for polar coordinates would be a polar grid, which looks like target practice. Instead of horizontal lines and vertical lines, you have lines through the origin and circles. And on each one of those things, one of the coordinates is held constant. And should you want one, you can actually buy a pad of polar graphing paper. And on most graphing programs, Desmos or Geogebra or whatever, you have the option of switching from a Cartesian grid to a polar one if you want to. These circles and the simplicity of representing a circle in polar coordinates, this one, for instance, really shows where polar coordinates shine. To represent this same graph in Cartesian coordinates, we have to write x squared plus y squared is 4. This is obviously much, much simpler. And polar coordinates are a godsend whenever we are analyzing either a geometric shape or physical motion that involves some kind of central symmetry like this. Circles, or something where a point is orbiting another point, even in some strange manner, or what have you. But I want to turn next to the problem of actually graphing a polar function, something of the form r equals f of theta. This is kind of like your old familiar y equals f of x, but here we're thinking of the r component as a function of theta. And graphing a few of these guys by hand is, I think, actually very productive practice. Not that you'll be graphing polar graphs by hand all the time in your future. You almost certainly won't. But it really helps you internalize the idea of how polar coordinates work. And again, because the subject is dripping with trigonometry, makes for a great trigonometry review. So let's do an example. Let's sketch a graph of this polar equation. R equals 1 plus sine of 2 theta. Now, as I mentioned in the book, anytime we're thinking of a polar function like this, it helps to think dynamically. R is a function of theta, so imagine theta running through all its values. Starting at 0, we've got the ray in its initial position, and then it increases more, and so we can think of that ray as rotating around the pole. And as it does, we are imagining a point that slides around on it, and that point is determined by this formula. At any particular angle, theta, well, we double that angle, take the sine of it, add 1 to it, and whatever number we get, that's our r value. That's where the point will be. And you can think about it as like a pen sliding around on that ray. As the ray is rotating, the pen is sliding up and down, and the combined effect is that we have this point tracing out some kind of a curve as we go. It's often a useful picture to have in your head. But for the actual problem of graphing one of these guys by hand, I think the most useful technique is to start with what I called in the book a Cartesian blueprint of the graph. The idea is that we start off by graphing this thing as though it were an ordinary Cartesian graph, where for some perverse reason we decided to call x and y theta and r, but everything is still on a perfectly normal rectangular grid. Doing this actually makes it easy to get the genuine polar graph because we'll be able to read it right off of the Cartesian blueprint. And this is a problem we already know how to solve from a trigonometry class. If this equation had been y equals 1 plus sine 2x, you'd have, I hope, no problem graphing it. So let's review how we might do that. Let me do a little scratch work over here. We know what the graph of sine theta looks like. Everyone knows what that looks like. It starts at 0, you've got a period that lasts 2 pi. That means it crosses the axis here at pi. Of course, the amplitude is 1, and we could fill in more detail if we needed it. As always, we start with what we know and make adjustments to get to what we want. What happens if, for theta, we substitute 2 theta? Well, now it's a different equation, so we'll need a different graph. Hopefully you remember from pre-calculus or earlier calculus classes that a substitution like that, changing theta to 2 theta everywhere in an equation, compresses the graph horizontally to half of what it was before, so that it'll run through a full period not in 2 pi, but in pi. Or just thinking physically, putting that 2 in there speeds this thing up. It completes a whole cycle when the argument of sine gets to 2 pi, but that will happen when theta is only pi if we already have a 2 in there. So the effect will be it will whip through a full cycle in pi instead of 2 pi. I could draw it like that, or I could save a little ink by just changing my horizontal axis. So there's a full cycle which takes pi, half of it is done in pi over 2. Okay. And now what happens when I put the cherry on top, the 1 plus? Well, everyone knows that. That means that for all the same theta values, the corresponding y values are all increased by 1. That means that the whole graph just shifts up by 1 unit. So instead of going between -1 and 1, it will go between 0 and 2, like that. All right, so that's basically the graph we're looking for, so let me put that over here. That should do the job. We may find, when we're transferring things over from the blueprint to the real polar graph, that we need to extend this further, but once we have one full period on the blueprint, it's easy enough to do that. So let's just keep it like this for now, and now I'll show you how to transfer it over to the actual polar graph of this equation. We want to go back to that dynamic picture of the ray rotating around the pole here, and the pen sliding around tracing out some kind of a curve. And while this whole thing is a bit intimidating to think of all at once, if we break it up into bite-sized pieces, it will be easy, thanks to this. For example, let's just think about what happens when the ray rotates from 0 to pi over 4. Why pi over 4? Because I know exactly what the graph does on that interval. I know what the Cartesian blueprint does. The r value goes from 1 up to 2. When theta is 0, r is 1. So when we come over here, when theta is 0, the moving pen is at 1. So it'll begin at this point. And as the ray rotates from 0 to an angle of pi over 4, what happens to the moving point? It goes from an r value of 1 up to an r value of 2. So as the ray rotates, the point is getting further and further from the origin until it ends up 2 units away. Maybe I'll go ahead and put some polar coordinates on these points. That will at least give us a sense of scale. And the curve is going to look something like this, and it's moving in this direction. Good. So we understand this segment between 0 and pi over 4. Well, now we'll just move on to the next bite-sized chunk, as theta goes from pi over 4 to pi over 2. As we traverse that interval, r starts at 2 and comes down to a value of 1. So as this ray sweeps out that space, this point, which started 2 units from the origin, is going to end up only 1 unit from the origin, somewhere over here. So maybe our curve continues like this. And I often find it helps to put little symbols, like this little arrow right here, to kind of match up the parts. Like maybe I'll put that one arrow over here and a double arrow here. So now we can see the correspondence between these two things very easily. If the arrows get too cumbersome, we can switch to different colors or whatever you want. Let's move on to the next chunk, which maybe I'll go ahead and mark with 3 arrows here, as we go from pi over 2 to 3 pi over 4. So here we're thinking about the ray rotating from pi over 2 down to 3 pi over 4. As we do so, the value of r, the distance from the pole, goes from 1 down to 0. So we're going to see this thing, as this ray is rotating, the point is getting closer and closer to the origin and finally hits it when we reach 3 pi over 4. So maybe something like this. And then here, as we go from 3 pi over 4 up to pi, r is going from 0 up to 1. So over in this picture, as this ray rotates like this point, which had been moving along so nicely and smoothly, something weird happens, and it takes this abrupt turn and kind of bounces out like this. Well, so be it. But that sharp corner, that cusp, it makes me think that something unpleasant happens to the derivative, or what might pass for a derivative, or what exactly do we mean by a derivative in this polar context? Stay tuned for next time when we'll be doing polar coordinates with calculus. Maybe we'll revisit this point and see what's going on there. But for now, all we care about is the graph of this thing, and we see what happens here. Well, clearly that's not the end of the graph. It continues on, so maybe I'd better extend my Cartesian blueprint after all. And I am not going to be able to distinguish 4 arrows from 5 at a glance, so let's do blue arrows, and I'll make them triangles to add another distinction for anyone who may be colorblind out there. As we go from pi to 5 pi over 4, our r value goes from 1 back up to 2. So over here, as we go from theta equals pi to theta equals pi over 4, the ray is rotating and the point is moving from 1 unit away to 2 units away. And now we can kind of get a feel for what the whole thing is going to look like. It's going to end up repeating over here what we initially did over here. It was that 2 theta that we substituted for theta that reduced the period of the blueprint to pi, but that means that it only covered where the ray rotated from 0 to pi. We still need to rotate the rest of the way, and the same basic pattern is going to unfold as we go from 5 pi over 4 to 3 pi over 2. In other words, in this little bit right here, the r value is going to go from 2 back down to 1. Like this. And as we go from 3 pi over 2 to 7 pi over 4, the r value goes from 1 down to 0. So the ray is sweeping out like this, and the point is coming in like that. And guess what happens on the last little bit? Yep, you guessed correctly. And once again, we got that surprising kind of bounce there. Anyway, that is the basic idea for how you can sketch a graph of a polar function by hand. Once you do it a few times, you'll have the hang of it. You'll get to review some trigonometry on the way, which is a nice side benefit, and you will, I hope, internalize a lot of ideas about polar coordinates. Including, it didn't happen in this example, but if our Cartesian blueprint dips under the theta axis, that would mean we would get some negative r's, which would mean that while our ray was rotating, the point ends up on the opposite side. You'll see a problem or two like that in the homework, but nothing is fundamentally different about it. One last thing I will say is that I encourage you to mess around with a computer program. Desmos is very good for this. That will allow you to graph polar functions. They can be a pain to produce by hand, as we've seen, even of this relatively simple one, but a computer can do it very quickly for you. It won't give you the insights you gain from doing a few by hand, but it will show you a nice range of the possibilities out there, things that you would never want to do by hand. So have some fun with that stuff, and I hope it brings you inspiration and insight of its own sort. And I think I will stop this video here. So, good day, good night, good afternoon. I have no idea what time you're watching this. Have a nice day, have a nice weekend. Merry Christmas, Happy New Year, have a nice life.
Okay, a quick addendum. Just for you, I jumped onto Geogebra and created a little animation in which you will see the rotating ray sweeping through this polar grid and that blue point moving on it, tracing out the graph of r equals 1 plus sine 2 theta, the graph we worked with at the end of the video. Are you ready? Of course you are. On your mark, get set, go! And there it is. There is the little weird bounce. And here it comes back around for the second bounce. And that's it. And the curve would get traced out over and over and over again. And if you follow the moving point, it looks like it's lurching around in this drunken manner. But if you forget about that and just look at the ray, you will see that it's sweeping out the space at an even pace the whole way around. And let's do it one more time, but this time I'll show you the point actually tracing out the curve. On your mark, get set, go! with that, I leave you.